Okay. And I did so I did some work last time. So actually, so yesterday I just streamed a little cuz I was like figuring stuff out on function calls. Um so so I went ahead and I just streamed it. So I was also thinking like, I can stream some of this. I mean, you don't necessarily have to be on. Like, it's fine.
Okay.
I might stream extra stuff, right? Just like building stuff, go through some stuff,
Heck yeah.
just to have more stuff out there. And now I'm, of course, I'm moving all my videos that were of me and my kids to not be public on my YouTube channel, so they're unlisted. So
Yeah. So the fam can still get to them and whatnot. Yeah.
yeah, not that they're. I know there's like birthday messages and
Yeah, just random stuff on there.
silly stuff. Did you want to use Twitch or YouTube to watch?
I'm looking at Twitch right now, and it
Okay.
seems holding steady. So we're just gonna run with that.
All right. Well, that seems fine.
The delay seems to be shorter with Twitch than it is with.
Oh yeah, I think that's true. I think uh, I think that's the case. And I also hopefully my chat is working. So
Um, I don't know. I don't get on Twitch very much, so I don't even know where to look, to be honest.
I think it's on the side. But anyway,
Yeah, there we go. It's up. Yeah, it's working.
yeah. So I'll try and pay attention to that in case people come in and ask questions. But yeah, we'll do our hard stop at your time, and that works for me. All right. Function one. I also have a nice stand-up desk, so that's good for a while. I'll stand
Oh
up.
yeah. Yeah. Well, who makes yours?
Well, so I bought it's actually a work table,
Ah,
like
so do I.
so it's I spent less on it than the normal one. The only downside is that it's not electric yet, so I'm gonna. So I actually 3D printed a piece that fits it. Oh,
Husky.
yeah,
Yeah, I got the same thing. It works great.
yeah. It's a little wobbly, but it's fine. Like I don't know. Anyway, like so I have a it's right here.
A little stepper motor, yeah.
Yeah. So I want to make a program and put it on my Arduino to make it go up and down because I don't know about you, but like the whatever the thing that held this in doesn't hold it in very well.
The
So like
screw.
yeah, I have a new bolt in it, but it's just it'd be cool. Plus it'd be eventually I want to do a CNC machine, like custom,
Oh yeah.
build it
I
myself.
use I just go and grab my Milwaukee, which is in the room next door.
I have done that. Yes,
It
that
works great.
is that is another way to do it.
4 man automated desk right there.
Yeah.
Motorized desk.
Well, we're too cheap to buy the automatic ones, but we can do it
Dude, those
ourselves,
things are
right?
pricey though, like $800,000 or something like that. Like these little workbenches are nice. I ended up buying another one.
Oh, did you?
Yeah, for the actual shop, yeah, because it was nice to have something you could adjust. Like I even ended up with a table saw all the time. It's so handy for that.
Oh, yeah. And the Husky one, it wasn't. I mean, it was like $100 or
Yeah, it was like 215, I think.
yeah, it wasn't too bad. All right. So I did update. So I think I pushed most of this to GitHub. So I
Okay.
updated it to sort of give us some sort of guidance on what the function arguments are typically they need to be. And then I got a little bit here on I figured out some stuff before you call printing functions. So what I thought today is we could write a couple simple functions given the time, and we'll see how that goes.
Okay. Maybe make it a skosh bigger.
That big enough?
Perfect. Yep.
All right. So let's suppose we have function A. So the things that we're going to normally do, and when you look at a regular function, is you've got this sort of your prologue, which sort of goes at the beginning, and your epilogue that goes at the end. And so those you can, I'm good at copy pasting. Indentation doesn't necessarily matter. I typically indent things so that it's readable.
Yeah.
Because otherwise everything in a line, I mean, a lot of stuff will be in a line, but especially when you get to doing loops, right? It's gives you a visual interpretation of what's going on. Okay. So let's suppose that we want to call this function, and let's suppose that we want to add up the first, say, 4 arguments, right, that are in the function. So out here, we might do something like move RA, let's see. So argument 1 is RDI, so we'd say move RDI, and some number, 0x, say 3, move RSI, so that's the second one.
Because you go backwards, right?
Well, and when you're doing the parameters, like I'm looking at this to determine which ones I need to do. We don't have to do them in that order because we're passing by registers. When you get to arg7 here, then you have to do it backwards. You have to push the things onto the stack in the reverse order. But because they're registers, like a register is a register is a register. So like,
right. It's always in the spot.
Yeah. So that part doesn't affect. It's just which ones do I use? So let's see. RDI is 1. This is 2. I could do move RCX. This is actually argument 4. And let's see, move RDX. Yeah, I'm just putting some numbers in. This is technically argument 3, right? And I could have done them in the reverse order, same order. What a compiler will do is it will pick them out in the appropriate order, right? So if it sees the 1 argument, it knows it's RDI. 2 arguments, RSI, RDI, so on and so forth.
Okay.
So then I can call function A in order to go ahead and do that thing that I want to do, right? And I put these here, like we don't need to keep this, but we'll keep maybe part of it. First 4 arguments. So if we're going to add them up, right, and the sort of result goes in RAX, I might as well use RAX. So I can do something like move RAX RCX. So that's one of my arguments. Add RAX RDX. Add each one of these in turn. And now they're all stored in RAX, which is our result. And then that's what we're going to return, right? So when you do the return in C, it's just whatever's in RAX. So I use these because, of course, it's
so it's returning the RBP then, right?
So, I mean, I'm not doing anything. I'm not doing anything in here. Like I'm using RBP and RSP. Technically, I don't even need to save those because I'm not touching the stack. I'm not doing anything. Like a typical function will save them right in this way. But RAX is our return result. Like that's where the return goes. If we look in, Godbolt, bring that up. Oh, these are long. A, long B, long C. Oh, what's it complaining about? Oh. I have something else called foo. Oh, super.
Is that yeah?
So here what it's doing is it's saving these registers onto the stack. All right, so pick different spots in order to save them. And then it loaded, like I did, right? It loaded the first one into RAX. And then it added, right? So it added them all up. And then REX is our return result. So that's that return statement. And then
it's stuck behind your picture. Sorry. Sorry to keep interrupting you.
No, you're fine. I should do a better job of knowing where my picture is. Is that better?
A little more to the left. There
we go. I should just put it.
Perfect, right there.
Put it over here. All right, so they take and they take all the registers, save them to the stack, do the move for the first one, and add for all the rest of them.
Okay.
And then because they use the stack, they pop RBP because it's pointing to the right spot, and then they do a return. So they didn't even so they didn't subtract because there is a notion of like there's no use subtracting if you didn't move the stack pointer back down, right? We didn't have any local variables. All we did is some computation.
All right.
So does that make sense?
Yep, that makes sense.
All right, so this is a pretty straightforward function, right? We're calling it, and then we could do something like move. Let's see. Let's print it off. So we define a string, maybe. %d new line 0 terminated. So we've got our sum. So, oh gosh, now I forgot, of course, my order. Let's look. All right, so RDI, then RSI. Okay. Move RDI. Message. Yeah, the value in RAX. Yeah, RDI is our string, and then RSI. RDI is our string. RSI is the thing we want to call, and then we need to call F. There we go. And I talked about this part before, right? With respect to PLT.
I think you did, but I don't remember what it was.
Right. So remember, in the 64-bit, right, your binary could be moved somewhere. So if you link against printf, you say, I'm going to use printf. So it puts one entry in there that says printf is located at 0x AABBCD, whatever, right? And then when you go and call that function, the operating system, when it loads your binary, it will replace the address, the fake address that's in there, with the real address of where printf is. And so it only has to replace that one spot instead of finding the 17 spots
Yep.
where you called printf if you're relocating a binary. So
Okay.
procedure linking table. So it basically allows you to call a function that's somewhere else, even though you don't know where it is. The OS says, I'll take care of telling you where this thing goes. So I think, I gotta say, that's global. There we go. I think it's global. No, it's not.
It's
Extern.
not.
It might be extern. Yeah. All right. And then if we run function 1, and my values are in hex, so of course they're
Some crazy number. Yeah.
Yeah. All right, so this is kind of like our simplest, function that we can call. I think slightly more complicated one might be that we take, we call another function, right? So maybe this function calls something else. Part of the library that I wrote, prints off, stuff in hex. So I think we can make a print a value in hex and maybe print a value in regular, like human
readable.
Yeah. So let's call it print hex. All right. So if we assume that our value is in RAX, when you go to print it, we're going to, at the top, we'll define our format. So I'll define both of them here. So hex message equals, okay, let's do, so we're going to be printing 16-bit numbers. So I think I want 0 leading 16 possible digits. I think I have to use an L and then an uppercase X. So L is long, which means it's going to try and do 64 bits. This is all like C stuff. And X, I think, is to use hex format. And then we'll do the same thing, except the DECIMAL. Is that right? I think that's right.
Yep, for decimal. Yeah.
I think. I think %L should work for long. So this is a. Okay, we'll start with hex and we'll work our way up. All right. So again, we have RDI. It's going to be our message. So we're going to do something. We're going to move RDI hex message. Move RSI, whatever's in RAX. That's what we'll just assume. Oh no. Let's assume a normal thing. I normally do it in EAX, but let's use the real one. It's actually RDI. Right, so if you if you're going to use this like a standard function, the first argument, so if I wanted to use it in, say, my C program that's outside of this, and we'll do it the right way. I normally just did it RAX, but we don't have to do that. All right, so RDI is going to have the first argument, the number we want to print. We're going to copy that to RSI and then copy our the message we want to print, and then we'll call printf. And stop me at any point if I go too fast.
No, it makes sense. So you're just You're just sending it to hex message, so then it can then get called, right?
Yep.
Okay. Yeah, I'm on track.
Yep. So now the sort of thing that we want to do is, we want to be able to call this and not have it trash all of our other registers that we're looking at. So the registers that we use, we're going to want to save. So I'm using push RSI, push RDI. Technically, I may not have to save these, but what you'll see in code is you'll see it saving registers, right, that it uses when you get to sort of more complicated things. So I want to sort of build that in as a practice of what we would do. And then push RAX, because when you call printf, right, it actually returns a result saying, was it successful or not?
Right. So that'll overwrite. Yeah.
That'll overwrite it. So to sort of just emulate what good practice would be if I were an assembly programmer and I wanted to adhere to, not destroying things, right? This is what I would do, right? So at the end, we'd say pop RAX, pop RDI, so reverse order, pop RSI.
That's fine.
Now, probably I don't need to save these because they're technically assumed to be destroyed, at least one of them, right? RDI, your compiler assumes that that's going to get destroyed because it's the argument, right? That's just how it should work. And let's see. So I don't know. Do you do a lot of terminal work?
Yeah.
So I like using the ampersands because then if the stinking thing fails, doesn't try and do
the other thing.
All right. So what did I? First of all, I probably didn't hit save. So and I put equals db. Okay. Let's try that again. Oh, and I did fix this in my file. On clean, if you do -f, it won't complain about files that don't exist.
Yeah.
Which is interesting. All right. So, and I think I was going to illustrate this, but let's see if this works. Let's do that one. Oh, it did seem it was fine. So there are some situations where you have to have, like I was testing it, and you have to have the stack aligned at a certain level. But apparently, that was interesting. Oh, I'm not calling it. That's why. Okay, let's go ahead and call it. So if we do move RDI, let's pick some value, 0x, feed beef, since you like beef. And then we can say call print hex. So it should, there we go. So what's happening here is that when I'll show you the solution and I'll should describe it. Sub RSP8 add RSP8. There we go. So in order to, I think it's either to make things faster or make attacks harder. I don't recall which one specifically was the case. What they do is they force it so that when you call a function like printf, that the address has to have a 0 at the end, right? And if you push, say, an odd number of things onto the stack, so if it starts with a 0 and you push an odd number of things, it'll end in an 8, right? So base 16, each one of those is 8. And so if it's an odd number, it'll end in an 8. And if it's an even number, it'll end in a 0 because it'll be a 10 in hex, 10 base 16. And so if you don't do that, then it basically will crash the program. So the OS or something like that is saying, oh, well, you called a function and you didn't do it on an even byte, a 0
Right.
at the end boundary, you're going to crash. And I spent, this was my stream the other day. It's been a while, like I knew it was a thing because I've seen it before, but I had to figure out, okay, what boundary does it have to be? Is it 8? Is it 16? So on and so forth.
Okay.
So when you get into writing a function and saving them, right, that's what we have. And if we say global on print hex, then we should be able to, in our C program, say that we have let's say a void function, print hex. It takes a long Z, whatever. This is our definition of it.
Mm-hmm.
And then we can just say print hex. And I could say, let's suggest return status. That might work. Let's look. There you go. We could pick some number.
What? Oh, sorry. Okay.
No, go ahead.
I saw the zero. I saw the zeros in there, and I was like, that doesn't make any sense, but it does now.
Yeah.
So because you grabbed just a return value, and there wasn't a return value in it before, which is why you got.
Yep. Well, so
Okay.
it's actually so this set it equal to 0. So that was the last place it got set.
Okay.
Right? And then, we did this called print hex, which we saved REX in both spots. So that got sort of kept over. But yeah, I mean, yeah, if you're not sort of familiar, right? Okay, that return result was actually, from the return of main, ASM main, which, okay, where was the last place it got set? Well, it got set right here. If we didn't have this, it actually would probably be.
So random, whatever was sitting in the address before.
Well, it would probably be the return result of printf. Right, so from, let's pull this over. Right, so I called printf right here. So EAX should have the return result from printf. And when I called print hex, right, I saved it and then restored it. So the last place that it got set was inside of that printf, I think. Which I think it actually would still be. Oh, I gotta change this to return status. Well, it's actually 10, which is. Oh, maybe printf. We could look at the docs on it. It's probably the number of characters printed, or yeah. Man, printf. Let's see. Oh, no. I think I'm right. Upon successful return, these functions return the number of characters printed, excluding null bytes at the end of the output. So when I print it off, I'm guessing that this text right here is 10 characters. No, that is not. Huh.
Would it be
'Cause that's what
spaces don't count, do they? No.
Oh, is that 10?
The new line, spaces in the new
That's
line?
10 hex, which is 16. Because we printed hex, right? So it just happened that it was 16 characters.
Oh, it's the value of 16 in hex.
Yeah. So
Oh, okay. It's like that
10
doesn't make
hex.
sense. 10 doesn't equal 16.
Yeah, if
It
we
doesn't.
did and then run it 1D, which if I took this, oh, where did I put it? There we go. word count, echo that, put in word count minus character 29, which I think is hex 29 base 10. No, it's hex 1. Oh gosh. Hex 1D base 10 29. Winner, winner, chicken dinner.
All right.
It did the thing it said it did. And so that, I mean, this is a, I mean, so we wrote a function, right? We're able to print it off, right? So this one didn't have many arguments. So I think we'll start, let's start with the, we got time. If you're willing, we can write a function that tries and print as many registers as we get. We can figure out how to print if you want to do that.
Yeah, let's do it.
Okay.
Let's do it.
All right. I'll make sure we won't need this for a little while. Because what we'll do is we'll actually pull this into the library when we get it all done, and then we'll be able to just like you're going through your program and like something's broken, you're like,
You just dump all the registers.
Dump all the registers. So it's gonna be involved though. All right, let me grab that. This is gonna help me. Okay. Dump registers. Okay, so we won't have any arguments, right, for our function. It's been watching all the code that I do. I actually did a bunch of them here. Okay. This is actually fine. So because we're going to be modifying a bunch, right? We're going to modify, because we got to call printf. So we got to use RSI, RDI, right? RSI for RDI for our print string format. And then we got to fill up all 6 registers, but we're wanting to print off what the values of them were. So we're going to have to
put them somewhere else.
Do a little magic, right? So we're actually going to put them on the stack here. So we're saving all of these, and then we can reference from either from RBP or ESP or RSP. We can reference them. So RSP, right, we're going up, so it's plus numbers. RBP would be going down, so it'd be negative numbers. It doesn't matter to me, but so let's start. We'll just start. DB. Okay, so let's start with RAX. I'm going to use a colon, and then I'm going to grab this format string here. BX. Let's see how many does it give me that are good. I think I want to break this visually so I can see them all. And the nice thing about the assembly is I can actually, like, it doesn't care about my new lines here, so this should be fine. I do want to put a space after these. I want them to line up. And R9 and R8 are the oddballs that are only two characters. So that should be okay. All right. So, arguments. Let's see. I'm going to copy this and make it a comment down here so I can look at both at the same time. Okay. And then, so we can see that. So we want to move into RDI, our message. Okay. Move into RSI. So the first one that we're printing
is RBX. Or no, RAX. Sorry.
RAX. So move into RSI. So I'm going to try and do this in an efficient way. So if I haven't overwritten it, we're going to use it. Hopefully. RIX. Move into RDX. So I need RBX. Okay. RCX. AB. Okay, so it's the same thing. I'm going to put it. It's same. Okay. So we got A, B, C. Let's do D. Oh, but that goes into RCX, RDX, R8, RDX. Okay. Move R9. Okay, so we need to move into R9. Oh, R8, that should work. And then I'm overriding it down here, so that worked out well. All right, so R8, R9. Okay, now we got to do... we got to push our arguments in our reverse order. So we got to pick a sacrificial register.
What would be R15?
Well, I think that's fine. It doesn't matter. So what we're going to do is we're going to move a value into there, and then so the one restriction that we have is you can't just copy memory location to memory location. So right now, right, we want to copy data. So A, B, C, D, R8. We want to copy R9. Oh, but I haven't destroyed R9, so actually I can just do this directly. So I could do a push R9 because I haven't destroyed it yet, right? R10, right, is next. So I should be able to do push R10. I think I can I should be able to push most of these, I guess. R11. So some of the time, right, yeah, we're okay. Like, it's just, you may not have to reference any of them other than RBP and RSP. But anyway, I guess we don't have those in our.
I'm about to say they're not in that list. They're at the top, but those are.
My Jippity didn't put them in the list. We'll do them. Let's get version 1 and then we'll do version 2 with those.
Okay.
All right, so push R13. Oh. I'm trying to remember what. Which is already pushed, but I don't want to mess anything up. Okay. So I think that's what I need there. So then, I could do a pop on all of these, but that sort of would not be.
Well, doesn't it do it below?
What?
Isn't it popping it below?
Well, so all of these are just saving my registers.
Okay. Oh, you gotta pop them before you add.
Which, yeah, so I pushed on all of these, right? And so one way you could do it is popping them all. But what I'll probably do is, right, so all these pushes do a sub, right? So I can just do one add RSP and then figure out how much I need, right? So I got This is 10 hex, 20 hex, 30 hex, 38. So 0x. So I just took and added 8, right? And two 8-byte registers is 16 bytes. And when you convert that to hex, that's 10 in hex. So if I do hex 38, so I got, this is 8. Each one of these is 8. 16
All right, so 18
equals 0x10, right? And then 20,
40.
38. So,
Oh,
because I only have one, right? I was doing every other, right? So this would be 18 in hex. This would be 28 in hex.
oh, if you went R16, if that existed, then it would have been.
Yep. Yeah. We'll do something where we count in decimal and hex, and maybe that'll be helpful.
Okay.
Okay. So if I could pop all of those, right? And I could pop them into the same register. I could pop them into a different register. Doesn't really matter. Or I can just do an add to say I'm going to negate, right, the effect of all these pushes, right? And you'll see the compiler will do this. It might even, if it's got local variables, it'll do a sub up here, and then in the bottom and do an add, right, to sort of counteract that. So, and you'll see that in code all the time. So that's, we're just being a little verbose. I don't know if I checked if this was on a. Did we get the right number of bytes? Let's see. So I think. Let's just count. So this is 1, 2, 3, 4, 5. So it'd have to be 1, 2, 3. So that's even. 1, 2, 3, 4, 5, 6. It's like 7, 9, 10, 11, 12, 13, 14, 15. So that's, I think it odd in that it, I think the call, right, pushes one onto the stack. So this needs to be odd, which it is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So I think that one is fine. And then I think I have an odd number here. So I probably need to do a sub RSP 0x8. And then I'm going to do this just so it's the same, but if I'm wrong, I think I counted right, but it's possible that I'm wrong. 8. Oh.
Is it not like the new line?
Yeah. I mean, it doesn't matter. It's like I'm just put as a label, but it should be fine. I wanted to be able to read it. Okay, so it compiled. We didn't call it. So let's take out all this stuff. We'll just comment this out. Call dump registers. Moment of truth.
Yay.
Oh. Did we not? Huh. Oh, we didn't call printf. Oh, of course. All right. Call printf. Hey, we got the stack right. Like,
yeah.
So if we got that wrong, it would have crashed. 100%. Oh, look at that. Actually, let's put a new line in here. And then when we call it, hey, okay.
Oh, that's so clean and pretty.
I cannot believe we got it first try. Mostly first try. All right, let's do RSP and R. I want to double check. I'm trying to remember. RBP register. Register number. So, like, for example, on ARM, right, they call like a register, there's a register called the link register, and it's like its actual number is number 16, but everybody references it as the link register. Six. Not sure this is gonna tell me what they. I'll see it. It is. Let's see. Yeah. So like technically RSP is R4 and RBP is R5. Okay. So they're not. Like I said, the ARM one. I know it's kind of small. Sorry.
No, that's so good.
On the ARM one, right? They have like the same name. Like they have the numbered one versus the like human readable one.
Right.
So, but okay. So let's try and get. Where do you want to put those? Oh, should we have them at the top? Like, oh gosh, if we put them at the top, let's put them at the bottom for now. If we want to change it later,
Just add another
yeah.
statement right there below where the cursor's at. Yeah.
Start. The chat got me. RSP : Gotta take our new line out. Grab our format string. Okay. And we'll tab them over. Okay. So this one will be tricky. Okay. So I'm going to use something I'm going to blow away anyway. So I'm going to grab RDI, right? Because we're going to overwrite RDI. I think. Where did RDI? Did I skip it? Oh,
No.
yeah, those aren't there. RSI and RDI. I didn't. 1, 2, 3, 4, 5, 6. So there's 12. Yeah, we're missing RDI. So this is the. Oh, this would be great. Well, let's put them on the next line. RSI, RDI. I was like, why did I not? That should have been somewhere. There we go. Okay. Grab that line and copy that. I don't really like split screens are a pain.
Yeah.
Okay. So the next one is RSI. So we can say push RSI, push RDI. Oh, great. And we're going to add some more. All right.
So then that RSI would be what, 40?
Yeah. Well, so the thing is we have to pick one register to like clobber, because we got to copy. We have modified RSP and RBP a whole ton. So I think there's two ways to actually we can. Yeah. There's a way we can do it. So we can subtract. So the problem is I need to use the register, but I didn't want to destroy all my registers before I push them.
Right, because then it won't have the right value in there, correct?
Yep. So let's subtract. So I'm going to reserve space for RBP and RSP, right? So because those are my last two ones. So what I'm doing is I move the stack down. I'm going to push all my other stuff, and I can just pick one of them. Like I can go here. I'm going to put space in here, just as a comment, so we can make sure we get our thing right. But I'm going to put it down here, even though it really goes up there. So I want to move into RSI because I've already got my value for it. The value of ESP, let's do EBP. Sorry, ESP. We'll do this one first. So the value of the stack pointer before we came in was clear up here, right? But it's really, so I'm not going to worry about the fact that, well, so we called the function, so that pushed on 8 bytes. And then we push RBP, which is another 8 bytes. So this RBP plus 4, or sorry, 8. Return. Hey, we got a viewer on Twitch. Or no, YouTube. They're on YouTube. There we go. All right, so we have our return address on top of the stack, and then stack before call. Let me make that a comment. So this is plus 10 hex plus 14 hex or 18 hex. So what I'm going to do is I'm going to grab the value of RBP because that gives me sort of a place in time, right? And so if I grab that, go ahead.
You're just holding on to it for later.
Yeah, I have it there, but what I'm going to do is I'm going to use my base pointer to figure out where was my stack before we called this function, right? So
okay.
Because it's at a sort of a fixed point, right, which is why we have RBP. So I need to add 18 to get back to the place I needed to be. So I'm going to do move into RSI, the RBP
plus 18,
add RSI, so I have to do it. I have to add 18 hex. Right, so that gives me the calculated value, and now I need to put into these two slots. So let's see, this is at plus 8, plus 10, plus 8, plus 10 hex, plus 18 hex, plus 20 hex. So I need to move into the location of RSP plus 0x20, the value that's in RSI. So I can move RSI directly onto the stack without a push, instead of having to say I want to push the value that I need. So this is why this is complicated, right? Because I'm like, I like
Doing
made
you
a
off.
slot,
Yeah.
did some more stuff, and now I'm gonna like, okay, put this thing where it needs to go. So this should be for RSP. And then we got to do the old value of RBP, which we can move into RSI, RBP. We can then add, because I want to grab the value from right here. So that's RBP plus 8, right? RBP points right here. RBP plus 8 points to that. So I should be able to move, I should be able to add to RSI 8 hex. And then I want to move into, it could be RSI. Let's do RDI just because. The value that's at RSI. So because I push the value's on the stack, but RBP is just a pointer to the stack. So I added 8 to the pointer. And now I'm going to go get the value at that location and put it in RDI. And now I have to move into RSP plus 18 hex, the value that's in RDI, RBP. Yeah, this is why this is it's a lot easier when I only had 8 registers and not 16. So
Brain space stack's getting a little full.
yeah, and we're hopeful. Okay, well, we got a minute.
We got a minute. Keep going.
Let's see. Will it work? Oh.
Line 6. I don't know, was that 6? Am I reading that right?
It's line 97.
Oh, sorry, I was looking at the wrong line.
No, it's fine.
Yeah.
Oh, I had a comma there. Oh. All right. Oh. Oh, I forgot to fix our stack. Oh, I'll fix that for next time. Right, because we pushed some more things on. I think we had 20
down
more.
there and 111.
I'm guessing. I'm gonna guess 58. 58. We did it! Oh my gosh! It was only this many lines to print all our registers. Next time we'll go verify.
Fair enough.
So, all right. Well, it sounds like you had a hard out. So let's. I guess we'll call it a day. And like I said, I'll probably just do some other streams of mostly stuff we've already talked about. So it'll hopefully just be refresher, but just to get more videos out there and more examples without you necessarily having to be on. I think I'm just trying to keep giving, and if people like it, great. And if they don't, well, you got the free part. So
well, it's certainly helped. Like it's starting to click. I'm doing a lot of reading outside of this, and when it clicks, it's going to make a lot of sense. I don't think I'm quite there yet, but I'm getting close. I feel like so.
Yeah, after some practice, I think it'll start
to
make
make
sense.
Yeah, I'm definitely a hands-on person, so that makes sense.
Okay. All right.
All right, good sir.
Well, we'll talk to you in a couple weeks.
No, Tuesday I'm still here.
Tuesday,
it would be the following.
Okay.
Yeah, following week.
All right. Well, I'll see you on Tuesday then.
All right, sounds good. Take it easy, sir.
Bye.